What is dark matter, and why are astronomers so confident that it exists? The answer to the first question, we don't know right now. But astronomers have built up evidence that something that has mass but no light exists and is pervasive in the universe. This evidence starts with the Milky Way. When we map out the mass motions of the galaxy, its disk, towards the outer extremities, we see continued high circular velocities, which have no explanation in terms of Newton's law and Kepler's laws of motion. Basically, the light in the galaxy is distributed far more centrally than the mass as indicated by the motions. There are only two alternative explanations. One is that our theory of gravity is simply wrong, and that would be Newton's theory of gravity. Astronomers have considered the possibility that Newtonian gravity is incorrect or needs to be altered on very large scales. And it's important to remember that Newtonian theory is only verified experimentally on solar system scales. So on much larger scales like hundreds or thousands or hundreds of thousands of light years, we don't have a direct experimental test of the theory. If the force law deviated from inverse square by only a few percent, you could explain away dark matter. But that's not a trivial thing to do. Newtonian gravity has passed every test put to it over hundreds of years, except in the situation of very strong gravity where we need Einstein's superior theory. On large scales and for weak gravity, we think Newton's theory is an excellent theory. Astronomers haven't come up with anything better, and they're loath to discard it. The alternative is that there is mass that doesn't emit light on large scales in our galaxy and also in every other galaxy and in the space between galaxies. Evidence for this has slowly and steadily accumulated over 4 decades to the point where dark matter is now part of the furniture of extragalactic astronomy. Astronomers simply believe that it exists, and they're trying to find ways of understanding its physical nature. Let's look in a little more detail at how astronomers reach this conclusion for our galaxy in particular, but any spiral galaxy. One of the figures of merit of a galaxy is its mass-to-light ratio, the ratio of its stellar mass to its stellar luminosity. Because we understand well how stars evolve, the mean mass-to-light ratio of a stellar population is a well-determined number. What we see in our galaxy is that the mass-to-light ratio of the disk of the galaxy is much larger than can be explained by any simple stellar population. In terms of mass-to-light ratio, the mass-to-light ratio of normal stellar populations is higher than the value 1 that it would have for the Sun, because so many stars are dim dwarf stars. Typical mass-to-light ratios for old stellar populations are between 5 and 10. The calculated mass-to-light ratio for the Milky Way and other spiral galaxies is almost 10 times larger. If we want to estimate the mass of our galaxy, we simply apply Kepler's law. And we can do this very robustly for the mass within the solar orbit. Remember that the Sun orbits the disk of the galaxy about 2/3 of the way out to the visible edge of the galaxy. Using Kepler's law, the stellar mass interior to this orbit is about 2 times 10 to the 11 solar masses. 200 billion times the mass of the Sun. But the entire mass of the galaxy seems to be 10 times larger, 2 trillion solar masses. And most of that mass is inferred to be at larger scales than the Sun's orbit, so distributed to the periphery of the galaxy, even beyond its visible edge. When we're modeling the motions of galaxies, the indication for dark matter is not any subtle or small effect at the 5 or 10% level. It's dramatic. As you map the rotation speed of a galaxy out beyond the solar radius to the edge of the visible galaxy, and using gas clouds and diffuse stars, you can go even beyond. Remember, galaxies don't have sharp edges, so there are tracers of the mass motions beyond where we'd see the visible edge. If you do this, the dichotomy is stark. The rotation speeds predicted by Kepler's laws should have declined by factors of 3 or 4, moving beyond the visible edge. In fact, they're constant to the visible edge and even beyond into the thin gruel of intergalactic space. So this factor of disagreement is very large and cannot be easily explained away by experimental error. But rotation curves are not the only reason astronomers think dark matter exists. Other evidence has come from the exquisite imaging of the Hubble Space Telescope or other ground-based observatories able to make very sharp images of galaxies. Einstein's theory of gravity says that mass bends or deflects light, and the overall distribution of galaxies in the universe, and the mass associated with them, deflects light traveling through the universe. Think of the universe as a funhouse mirror with slight undulations caused by mass distributions that deviate light as it passes, subtly distorting images. This effect can be easily measured with large telescopes. It's quite subtle, just a few tenths of a percent deviation of the average shape of a galaxy caused by mass deflections along the way. But the sum of those deflections is another affirmation that some dark material exists not only within those galaxies, but in the space between them. Beautiful evidence that dark matter, or something like it, exists has come recently from observations of the great observatories, the Hubble Space Telescope and the Chandra X-ray Observatory. There are several situations in the distant universe, a few hundred million light years away, where two clusters have approached each other and passed through each other. The distance between galaxies is such that when clusters approach and pass through each other, the galaxies rarely collide. They simply interact by gravity and then continue on their way. However, there is hot gas in a cluster, and the gas is viscous, and so the gas belonging to two clusters heats up and emits X-rays and crashes into one pile. In at least two clusters, we've been able to observe the pileup of gas that emits X-rays, while the dark matter has continued and sailed on through in each of the clusters. The dark matter is measured by the gravitational lensing effect I just referred to. In these cases, it's excellent evidence that something like dark matter, which interacts extremely weakly with electromagnetic radiation, exists and forms most of the mass of each of these clusters. There's another reason that astronomers are fairly confident that dark matter exists, and it's based on theory and simulation. As computers have grown in their capabilities, we've been able to simulate larger and larger volumes of the universe. In particular, how, starting from smooth initial conditions, the clusters and galaxies could have formed in the first place, by simple gravitational effects. If, in a computer simulation, you fail to put in dark matter as an ingredient at the beginning of the simulation, you fail to produce anything that looks like the real universe we live in. Basically, the matter will crunch down onto small scales and produce too much structure early on. Dark matter mediates the formation of galaxies and clusters and produces the delicate filamentary structure of clustering that we observe in the actual universe. So without dark matter as an ingredient in the simulation fails to describe what we see, which is a reason that theorists are confident that dark matter exists. The evidence for dark matter is convincing. Based initially on rotation curves of spiral galaxies, it's been found in essentially every spiral and elliptical galaxy inspected, even down to dwarf galaxies. Additional evidence comes from gravitational lensing, which shows that dark matter not only exists in halos around galaxies, but it permeates intergalactic space.